when you sit down to write code and, you hit compile, how does the computer actually know what your code means?
Right. It's a really profound question. I mean, we expect computers to be perfectly logical, right?
Yeah.
But bridging that gap between human intent and machine execution is, well, it's still an enormous challenge.
Yeah.
We've mastered the surface level stuff, but the depths of meaning remain largely uncharted territory.
Completely. And as a student in CS330, programming languages and compilers, you've spent weeks defining the syntax of a language.
Okay.
You know how to use backus and form, you've built parsers, and you know how to validate the grammar of your code. But, syntax is really just spelling and grammar.
Right. It just tells a compiler if a sentence is constructed correctly.
Yeah, I can write a grammatically flawless sentence like, the purple silence barks loudly. The syntax checks out, but the meaning is just total nonsense.
Total nonsense. Syntax does not give the code its computational soul. And that is exactly what we are digging into today in this deep dive.
Right, using your notes for Class 20 dynamic semantics.
Yes. We're looking at the 3 major theoretical techniques researchers are using to actually capture the runtime meaning of programming languages.
But before we get into all the heavy theory, we really need to acknowledge the reality of the industry you're about to enter. Because there is this massive gap between the theory we're going to talk about today and the actual compiler you are building in your lab right now.
Oh, absolutely. Despite decades of computer science research, modern compiler designers still largely manage dynamic semantics entirely manually.
Wait, entirely manual?
Pretty much, yeah. Which means when you are writing a compiler, you are encoding dynamic semantics by generating templated assembly code for each individual operation in your abstract syntax tree.
Wow.
Yeah. You traverse the AST, you find an addition node, and you manually tell the compiler exactly which assembly instructions to spit out. You are the one manually enforcing the meaning step by step.
But, doing it manually, that introduces a terrifying amount of risk, doesn't it?
Oh, massive risk.
If a compiler developer makes a tiny logical error in translating a high-level concept into assembly instructions, that flaw gets baked into literally every single piece of software compiled with that tool.
Exactly. We have seen historical bugs where perfectly valid C code was compiled into machine code that silently dropped security checks.
Oh, wow.
Yeah, just because the compiler misunderstood the dynamic semantics of some weird edge case.
And that is exactly why finding a universally accepted automated way to formally encode dynamic semantics is still this massive unsolved frontier in computer science.
Right. If we could automate it the way we use attribute grammars for static semantics, we could mathematically guarantee that a compiler interprets our code exactly as intended every single time.
Which would be amazing.
It would change everything. So researchers have developed different paradigms to try and, trap this meaning.
So let's talk about those. The first approach researchers take is to really lean into the physical reality of the machine itself. If we can't use natural language to define what a statement does, maybe we can just watch the hardware.
Right.
And this is operational semantics.
Yeah, operational semantics.
Mm-hmm.
You can think of it as a very rigid state-machine approach. You figure out the meaning of a programming statement by looking at the exact state of the machine right before the code runs, and then looking at the state of the machine right after it finishes.
Okay, so just before and after.
Well, yes and no. If you collect all of those minute state changes throughout the execution of an entire program, you have completely defined the program's operation.
Right. I like to visualize it like a track race. A natural operational semantics is just looking at the starting line and the finish line.
Yeah.
You only really care about the ultimate final state of the system after the race is entirely over. But structural operational semantics is much more granular, right?
Yeah, way more granular. You are looking at every microscopic muscle twitch, every bead of sweat, and every single footstep along the track. You are documenting every tiny state change for every individual statement.
But if we think about applying structural operational semantics to, a modern computer, the sheer scale of the problem becomes overwhelming.
Oh, it's impossible. A single high-level statement in a language like Java creates an absolute tsunami of physical state changes.
Right, because a modern operating system has background processes running. It's managing the network stack, updating the display, shifting memory around.
Yeah, exactly. Trying to track the meaning of one line of your code amidst the chaos of a whole physical machine is impossible. There's just way too much noise.
But wait, I mean, if we're just mapping state changes on a virtual machine, aren't we just kicking the can down the road? Like, who defines the semantics for the virtual machine? Aren't we trapped in an infinite loop of definitions?
That is a very valid critique, and it's a known limitation of this approach. To avoid that infinite loop, researchers don't use real computers or complex, heavy virtual machines.
What do they use instead?
They use an intermediate language running on a highly constrained, specialized, purely theoretical machine.
Okay.
This intermediate language is a step higher than raw binary machine code, but much lower than a high-level programming language. The semantics of this theoretical machine are so painfully simple and primitive that they are universally agreed upon by mathematicians and computer scientists.
So the goal is to define your high-level statements using this primitive intermediate language, rigidly tying the meaning to unambiguous state changes.
Exactly.
Let's look at the C for loop example from the notes. Because, in a high-level language, a for loop hides a lot of mechanical complexity behind three simple expressions. You've got initialization, condition, and incrementation.
Right. And when we translate that into our primitive intermediate language to define its operational semantics, we strip away all that syntactical sugar.
We just break it down.
Yeah, we break it down into the only things our constrained virtual machine understands, which is basic operations, evaluating conditions to zero or non-zero, and raw jumps or go-to statements.
So the high-level for loop just gets dismantled. First, the initialization expression runs. Then, we manually create a label in the code to mark our spot.
Right, like a bookmark.
Next, we have to evaluate the condition. In our intermediate language, we write a primitive statement, like, if the condition evaluates to 0, meaning it's false, jump immediately to an exit label at the very bottom.
Spot on. And if the condition is not 0, the machine just falls through to the next instruction, which is the body of the loop.
Makes sense.
Once the body executes, the machine hits the increment expression. Finally, we issue a forceful, unconditional go-to command that sends the machine right back to the top label to check the condition again.
So by translating the high-level for loop into these primitive go-to and if statements, we've mapped it directly to the operations of our virtual machine.
Exactly.
There is no ambiguity left. We can see exactly how the state shifts at each tiny step.
It's a highly mechanical process. But as you pointed out, operational semantics is still fundamentally tied to the concept of a machine, even if it is a theoretical one. If operational semantics is too tied to the hardware, how do we guarantee a program won't crash before we deploy it? We have to abstract the machine away completely.
Which means we are leaving the realm of engineering and entering the realm of pure mathematics.
Yes, exactly.
And this brings us to denotational semantics. Here, we restrict our view of states strictly to the values held in the program's variables.
Right. No hardware, no go-to statements.
We are mapping program syntax directly to mathematical objects and recursive functions. The mathematical objects literally denote the meaning of the syntax.
And to pull this off, we have to formally redefine what state actually is. In denotational semantics, we set up a theoretical ledger. Let's call it a mapping function, or a var map.
Okay, var map.
This ledger keeps track of every variable and its current value. When a program starts at state 0, the ledger is completely blank.
Let's actually trace how this ledger updates using a tiny C program. Our first line of code is simply declaring an integer, just in x semicolon.
Okay, so the syntax int x triggers our var map function. We move to state 1. An entry is written into the ledger for the variable x. But because we haven't assigned it a value yet, its mathematical value is formally defined as undef.
Undefined. Got it. Next line, we declare a character and assign it. So char y equals a.
We move to state 2. The ledger now has two entries. X is still mapped to undef, and y is mapped to the character a.
Then we hit some basic math. Let's say x equals 5 plus 7.
The var-map function processes the addition mathematically. We transition to state 3. The ledger updates the entry for x, replacing undef with the enter 12, and the entry for y remains a.
Okay, and here's where I really want to pause because the notes have a tricky final line.
Oh, yeah.
The line is y equals y plus x plus plus.
Right.
We have a post-increment operator on x while simultaneously updating y. How does the mathematical ledger handle that kind of sequenced side effect without a physical processor to, execute it step by step?
That is the beauty of treating the language as a recursive mathematical function.
Yeah.
The expression is evaluated based on the rigorous rules of the mathematical model, not a CPU clock cycle.
Okay, so it just does the math.
Exactly. The function evaluates the right side using the values from state 3. Y is a, x is 12. It mathematically increments the character a by 12, resulting in the character m, and assigns that to y.
Oh, I see.
And because the model defines the post-increment operator to take effect after the evaluation, the function recursively calls itself to update x to 13.
Wow.
Yeah, so in state 4, the ledger is perfectly stable, x is mapped to 13, and y is mapped to m.
That's super clean. Your notes also highlight how this applies to something fundamental, like mapping a string of binary digits into an actual numeric value.
Right.
You can map the syntax of a binary string using recursive mathematical functions. A function processing the character 0 maps to the mathematical number 0. Processing 1 maps to the number 1.
Right, and if you have a longer string, it just recursively multiplies the previous value by 2 and adds the current digit.
It treats the entire programming language as a mathematical construct. You aren't running code, you are literally solving an equation.
Solving an equation, yeah.
But, I mean, if we have this elegant mathematical model, why are you and I not using compilers that automatically generate perfect software straight from these equations?
That's the dream, isn't it?
Yeah. If we can perfectly map syntax to a mathematical object, shouldn't we just feed that math into a generator and get a bug-free compiler?
Well, if we connect this to the bigger picture, you are describing the holy grail of computer science. But creating formal mathematical models and mapping functions for an entire complete programming language is incredibly daunting.
I can imagine.
Think about trying to write a pure mathematical function that perfectly models memory allocation, garbage collection, thread concurrency, and pointer arithmetic across an entire operating system.
Oh, that sounds like a nightmare.
It is. The mathematical model becomes so large and complex that it is fundamentally unusable.
So it works beautifully on paper for tiny, isolated examples. But the complexity just explodes when you try to scale it to a language like C++ or Rust.
Precisely. No one has successfully used denotational semantics to automatically generate a full compiler for a major commercial language.
That makes sense.
And from a practical standpoint, you wouldn't hand a junior developer a book of recursive mathematical mapping functions to teach them how a while loop works. It is conceptually brilliant, but pragmatically very limited.
So if denotational semantics fails to scale for full languages, and operational semantics is too bogged down by tracking state changes on a machine, how do we guarantee a program is mathematically correct without losing our minds?
Well, we have to abandon the concept of state entirely.
Just throw it out.
Throw it completely out. That brings us to our third approach, which is axiomatic semantics. This method throws away the ledger of variables in the virtual machine. Instead, it uses mathematical logic, specifically predicate calculus, to define constraints on the variables.
Predicate calculus sounds intense.
It sounds worse than it is. It just means we are using formal logic to evaluate true or false statements about our code. Every single statement gets surrounded by rigid logical boundaries.
Okay.
It gets a precondition, which is a logical constraint that absolutely must be true right before the statement executes. And it gets a postcondition, which is a logical constraint that is guaranteed to be true right after the statement executes.
I like to visualize this like setting up bowling alley bummers.
Oh, I like that.
Yeah, the bowling pins at the end of the lane are our postcondition. We need to knock them down. We don't actually care how the ball rolls down the lane.
Right.
We don't care about the friction of the wood, the oil pattern, or the exact rotation of the core of the ball, which would be the operational state. We just set up rigid logical bumpers on the left and the right to guarantee that the ball hits the pins. We are constraining the execution environment.
That is a really great analogy, but we have to take it a step further to understand how the math works. If the pins are the postcondition, your job in axiomatic semantics is to find the weakest precondition.
Weakest precondition.
Yeah. You are looking for the exact millimeter closest to the gutter where you can place the bumper and still mathematically guarantee a strike. You're working backward from the pins to the player.
Okay, let's ground this in the mathematical example from the notes. Imagine we have a postcondition we desperately need to achieve. We need a variable named sum to be greater than 1.
Okay.
So the logical expression sum is greater than 1 is our postcondition. And the line of code we are about to run to get there is sum equals 2 times x plus 1.
So we know the code and we know the desired result. We have to work backward to find the weakest precondition for the variable x. What is the absolute minimum constraint we must put on x before this code runs to guarantee our postcondition?
How do we find it?
To find it, we take the expression from our code, 2 times x plus 1, and substitute it into our postcondition wherever we see the variable sum.
Oh, okay. So the logic puzzle sum is greater than 1 becomes the mathematical inequality 2 times x plus 1 is greater than 1.
Exactly. And then we just solve for x.
So you subtract 1 from both sides, And you get 2 times x is greater than 0.
Right.
Divide by 2 and you arrive at x is greater than 0.
Yes. Therefore, your weakest precondition is the logical statement x is greater than 0. If you can mathematically prove that x is greater than 0 before that statement executes, you have absolute logical certainty that sum will be greater than 1 afterward.
Wow.
You have proven the code is correct without ever even running it.
That feels incredibly powerful. That is just one line of code. Software has millions of lines. How do you prove an entire program?
This is where we introduce inference rules. To evaluate a sequence of code, you have to chain these proofs together. If you can prove that precondition P1 running through statement S1 guarantees postcondition P2, you have your first link.
And then P2 becomes the precondition for the next statement, S2.
Exactly.
If P2 running through S2 guarantees postcondition P3, we can chain them. We can infer that starting with P1 and running S1 followed by S2 will absolutely guarantee P3. You're just chaining the bumpers down the entire length of the bowling lane.
Yes, but chaining simple statements is the easy part. The entire system hits a massive roadblock when we encounter loops.
Oh, right. Loops.
Yeah. An inference rule requires a known precondition and a known statement. But a loop runs an indeterminate number of times based on runtime data. You can't just chain P1 to P2 to P3 because you don't actually know how many times the loop will execute.
So how do you prove a loop?
You have to discover what is called a loop invariant.
Loop invariant?
Yes. This is a single universal logical truth that remains true before the loop starts, remains true after every single iteration of the loop, and remains true after the loop terminates.
That sounds tough.
It acts as a logical bridge across the chaos of the loop, whether it runs 0 times or 1,000,000 times.
Imagine trying to mathematically prove a while loop that is searching through an unsorted array of 10,000 user records to find a specific ID, defining a single mathematical logic statement that holds true regardless of where the ID is located, or if it even exists at all. That sounds incredibly difficult.
It is exhausting. Because of the nightmare of defining these loop invariants and chaining inference rules across thousands of lines of code, axiomatic semantics, much like the other methods, is currently only feasible for smaller, highly critical sections of code.
Like what?
Like the software running a pacemaker or a spacecraft navigation system. We cannot yet use it for full-scale automatic validation of a standard desktop application.
Wow. So we've explored 3 fascinating theoretical paradigms. Operational semantics gives us the rigid, isolated state machine. Denotational semantics gives us the elegant, recursive mathematical mapping. And axiomatic semantics gives us rigorous, boundary-driven logical proofs.
Right.
Yet none of them perfectly bridge the gap between formal proof and automated compiler generation for everyday software.
Which brings us right back to the lab. The automated dream of dynamic semantics remains an exciting, unsolved frontier. The software industry desperately needs a way to formally prove program correctness, to know without a shadow of a doubt that a banking system or an autonomous vehicle won't crash or produce a fatal error due to an unforeseen runtime state. But we just aren't there yet.
And because we're not there yet, compiler designers, including you, have to manage dynamic semantics manually.
Exactly.
You are writing the code that generates the templated assembly instructions. It requires a deep understanding of both the high-level theoretical intent and the gritty, low-level machine architecture.
It's an art form as much as it is a science. You are manually translating the computational soul.
And since you are managing this manually right now, let's take a look at where you are in the course. Today is Thursday, April 2nd, 2026. Looking at the CS330 syllabus, you should have already submitted your Week 9 journal.
Remember that the journal requires the 2-1 rule. You need a minimum of 2 thoughtful paragraphs and 1 quiz question for your peers to consider.
Right.
You should also have finished skimming chapters 8 and 9 of the Tane textbook, Introduction to Compilers and Language Design.
And crucially, your Lab 7, the B minor parser, was due earlier this week. We hope that abstract syntax tree is looking structured and ready for you to manually generate some assembly code in the next phase.
But the week isn't over. Tomorrow is Friday, April 3rd. Your perusal annotations for the Liskov video are due.
Don't forget those.
Professor Reed emphasizes that reading and viewing in this course shouldn't be passive. You need to be actively engaging with the material, questioning the concepts, and leaving those annotations.
Make sure you get those in tomorrow, because when we look back at the journey we took today, it fundamentally changes how you look at the code you write. You aren't just typing text into an editor. You are manipulating a complex system that the brightest minds in computer science are still struggling to perfectly mathematically define.
And that leads me to a final Slightly provocative thought for you to ponder before you head back to the lab.
Okay, let's hear it.
In the syllabus, there is a section detailing the use of large language models in the course. The professor allows for what is called vibe coding, using an AI to generate code snippets for your labs that you then review and tweak.
Right. I mean, we all do it. You prompt the LLM, it spits out a solution, and if it compiles, you just move on.
But think about the last 15 minutes. Human computer scientists have spent decades and still haven't found a universally accepted way to formally define and prove the meaning of a program's runtime semantics.
Yeah.
We cannot automatically guarantee that human-written code is completely correct.
Right.
Large language models do not construct internal mathematical proofs of dynamic semantics. They are incredibly sophisticated statistical engines predicting the next most likely token based on their training data.
So wait, if we cannot mathematically prove the semantics of the code we write ourselves,
How do we ever guarantee that the code an AI generates is mathematically sound and safe? If the AI does not understand the operational, denotational, or axiomatic semantics of what it is writing, and we lack the automated tools to prove its output is flawless, how much can we really trust it in critical systems?
that's a great point. It's one thing to have an AI generate syntax that successfully compiles. It is an entirely different universe to mathematically guarantee that the code's computational soul will not cause a catastrophic failure when it hits some unexpected edge case.
Exactly.
It is definitely something to think about the next time you use vibe coding and an AI hands you a script. Are you really sure what that code means?
It is the frontier of our field. And as you build your compilers, it will soon be your frontier to explore.
Keep asking those hard questions, keep that mind open in the lab, and remember, even if the compiler doesn't fully understand the computational soul of your code, you should. Good luck with those perusal annotations due tomorrow, and we will catch you on the next deep dive.